Hey everyone, I'm John, Renner, and hello, and I'm here to talk about NoSQL. So, for those of you who don't know, NoSQL is a database technology, and we're going to be digging around and all sorts of things that it does. It's really cool. To start off, lots of people are using NoSQL. We have Mozilla, LinkedIn, Facebook, Dig, Amazon, and Twitter, and many others are all using it. All the cool kids are doing it, and you should too. But first, a bit about SQL. If we're going to talk about something called NoSQL, we should probably know what SQL is, so what it means to not have it. So SQL is a interface for talking to relational databases. Relational database model, which basically means that you normalize all of your data and then include references to them. So that way you don't have to, when you update one thing, it's updated everywhere. And we'll see that in tables and stuff in a little bit. But there's some problems that SQL introduces. There's the object relational impedance mismatch, which is the idea that SQL does not represent data in the way that you really want to work with data, especially in object-oriented environments. Things like encapsulation, access control, things like that don't exist in SQL, which makes it sort of a pain to pull things out of the database and put them into your code. That's why we have things like ORMs, object relational mappers, to help us with this. It's still just a problem with using SQL. I also noticed at the top I call it the human interface, and it is. You write sentences to a database and ask it to give you back a result, which is very nice, except for when you actually want to build it into code, because you have to construct these templates of strings and start to populate them and send them in. So if I'm sitting at a terminal and just writing to the database, SQL's great. Gets a kind of a pain sometimes, otherwise. Like I said, it's schema-based, which basically every entry has a form that it has to take and has to follow. It makes it very easy to query, but it also puts restrictions on data that may or may not have all of that data. And it all revolves around the almighty join statement. Well, all of you are familiar with SQL, and I'm going to kind of brush through this, but I will explain what join does and why it's important. So, for example, in SQL, this is a good normalized database. I have three books, and 3 authors, and I want to sort of match them all up to the ones they belong to. And so I select everything from books, and I join authors on books author ID is equal to author's ID. So basically I'm just saying, all right, these two are linked, and these are linked. So what SQL does is it creates a giant table, and it says, all right, what are all the possible ways we can put these together? And that's sort of what we get, and it's like, okay, now what were my requirements? My requirements were that these 2 columns must equal each other. So it then pairs that back down to this, which is all really well and good. But if you notice, you have to pair up all of your data. And that becomes problematic when all of your data isn't in one place. When we start talking about distributing the system, that becomes really costly. So, CAP theory. CAP theory is a theory about distributed databases that says when you're building a database, you can only really pick 2 of these. One comes at the cost of, 2 come at the cost of the other one. So I can have a consistent database, meaning that the database looks the same from all angles. From wherever I'm accessing it, it's the same. And availability is that I can access it all the time, it's always up, I can get what I want from it. And partition tolerance is to say that once I have it running on several servers, if one goes down, the whole system stays up and I don't lose the ability to access things. So there's a SQL is built on the idea of ACID, atomic, consistent, isolated, and durable. That means that in building SQL databases, they've chosen consistency and accessibility. And not accessibility, availability. Basically, the idea here is that if it's atomic, consistent, isolated, and durable, that the data is not going to change. The data is the same from everywhere. All operations are done in their own sort of space, and nothing can conflict. That does great things, except for when we want to say, okay, now I want to run on 2 servers or 3 servers. I have a lot of users. See, this wasn't a problem when SQL first started showing up, because you didn't have websites like Facebook that say needed to serve, maybe 20 queries on every page for people who are browsing for hours and hours and hours. You just have load problems, so you need to start branching out. So a new model came up called BASE. Basically available, soft state, eventually consistent. And it sounds very wishy-washy, and it is. And it's a funny way they wanted to fit the ACID-based thing, and it's not the best acronym, but it kind of describes the way NoSQL is going to work. They decided that really what's more important than having the data always be the same, some mismatches are okay as long as your service is up. Because if your service is down, who cares if it's consistent? So instead, let's make it really easy to split it across a ton of servers and make sure it always stays up. and then we'll make sure that as it runs, it goes through and makes sure every once in a while it's consistent. So that brings us to NoSQL, which is running on the base ideology. And it comes down to 4 different types of databases, because NoSQL means not only SQL. It doesn't mean any one specific thing. So it's like if I went to you and said, hey, what are you going to build your project in? And I was like, oh, you know, not only Java. And it doesn't tell you anything, except that you're going to be hip and modern. So we're kind of going to go run through these and help understand a bit what's going on with all the different types of NoSQL databases we can have. So when you distribute a database, and I'm bouncing back a bit, I apologize, there are sort of 3 things you need to consider, or there's more than that, but these are some of them. Sharding. So when I have a database, I want to be able to split up data. I want to say this server is in charge of this much data, you know, and this one's in charge of this other section of data, and I can replicate that and do things to help keep it up. Master slave. So the idea is when I connect to a database, I have one endpoint that I'm going to. And that from there I need to figure out what's going on. So you can have master-slave relationships, which is, oh, I have like a master that controls all the rights to the others. Or I can have masterless, which is each database instance can handle the query and pass off what it needs to everyone else. Masterless tends to be a much nicer solution. It's not as possible with SQL. It's possible, but it's more opaque. And replication, basically you want to have several instances of everything that's up and running, so if one goes down, something can fail over, and your service stays up. So here's a bit of a diagram. It's sorry it's blurry, but it's the best one out there, so I had to blow it up a bit. So what we have here is we have 3 physical servers, M1, M2, and M3. Machine 1, 2, and 3. And we have 2 shards for our database. Our database is sharded into V1 and V2. So we have 2 halves, so think maybe it's usernames, and they're split by alphabetical, A to M and N to Z. So what we have now is we have, for each one, there is an instance of it on all 3 machines. So V1 is up here, V11, V12, and V13. And the way they're configured in this sense is that if any one machine goes down, the system still stays up, which is really, really cool. It ensures lots of nice, good things. So if you notice out here, we have this layer called the proxy and has a config DB. This is basically so that this is your access point, because you don't want to be talking directly to these machines, because, like we know, they can go down. So that wouldn't help me if I went to machine 3 when it was down. So you have the proxies that have nothing to do with this, except to point you in the right direction and tell you where to go. So now we can start talking about NoSQL, now that we've sort of built up a bit of vocabulary and understanding. So key value stores are the simplest of NoSQL databases. They're nice and easy. Think a hash map in database form. I have a key and a value, and I just ask for the key and I get it back out. Naturally, something that's that easy, if I have one key to access everything, it's very easy to shard, just split up into chunks. I can just say, oh, keys in this range go here, keys in this range go here, nice and easy. But then you get to the problem, how am I going to do a complex query on this? Like, what's going on here? So that's where MapReduce comes in, and we're going to have a lovely slide on MapReduce in just a second, so bear with me. And there's also the idea of how much can you store in that. So key value stores are really for shallow data. So if I'm going to have a string, a date, maybe an array or set, but you don't really want to have anything too deep in a key value store. The whole point is for it to be light and easily queryable. So React is a good example of one of these. React is a key value store. It uses HTTP as its interface. So HTTP already has the verbs for get, put, delete, all these things. So like, hey, why not use something that's already out there and a lot of things can already use to interface with our database? So in React, you have the idea of buckets and keys. So a bucket is sort of like a table, but less formal. So they call it a bucket. You kind of just throw stuff in it. And the key is the key that you're using to look it up. So when I do a query, I just ask for the bucket and the key, and it spits it back out to me. Now the interesting side effect of this is you could actually build a website in React. Not that you would want to, but you could. You could put web pages in and it could request, and it's just interesting. React supports all sorts of data types. It's built on Erlang, so you can store any Erlang data type in it. You can store any valid JSON type in it, and it also stores raw binary types. So you can throw your images into the database as well, if you are so inclined. React supports full text search, which is really its big selling point, in that I can set up nodes in my cluster that are purely in charge of controlling search. And I can search over all my values using queries without having to necessarily build a full MapReduce function set for it, which makes it really, really, really helpful. Usually you need someone external service to do this in a lot of databases. And it's open source because who doesn't love open source? So MapReduce. MapReduce is a way of comprehending data. I say query all data. Technically you don't have to. You can query subsets of data, but basically you're grabbing a chunk of data and you're saying, I want to draw a conclusion from this, or several conclusions from this. In some databases, MapReduce comes out in the form of queryable output, in that I can define a view, which is basically like another table that's dependent on other ones. And I can say, this view is going to be the result of MapReduces, and then I can query that, which is really, really helpful. It makes MapReduce really efficient and lets you create really kind of cool kind of queries. It's like pre-compiling queries. Problem with MapReduce is it's expensive. You are running over all of the elements and performing a function that could produce more elements than are there, maybe less, and then running another set of functions over all of those. So you don't really want to MapReduce everything you want in real time because it can just get expensive. So we're going to do a bit of a MapReduce example here. We're going to talk about friends of friends. All right, everyone up here has a friends, A, B, C, and D, or Andy, Brian, Chris, and Doreen. Yeah, it's clever. So what we're going to do is we're going to try to match them up and say, okay, what friends do Andy and Brian have in common? Or do Chris and Doreen have in common? So that's where we're going. So what we're going to do is we have a function here that's going to map. So it's going to take each row in here, and it's going to pair up two people in the row. So we have Doreen and Andy. And then we're going to emit. Emitting basically says we're going to set this up for the reduce function, which we'll get to. So basically what we do, so over here is what the result of the map functions. So for Andy, we pair him up with Brian and emit the rest, pair him up with Chris and emit the rest, and such like that. We're sure to keep these alphabetically ordered. I got away with that by using sets over there because they would be the same. But the idea is that that way they'll match up. And we'll see that in a second. Because if we have Andy and Doreen here, when we're starting from Andy, we want Andy and Doreen down here. We want them to be the same key. Because when it comes to reduce, they're going to get squished together. So once we have this lovely table, we go to the reduce function. Now, notice this changed a bit. What happened was we took all the things that were the same key and turned them into a list. So back, I'm going to step back a second. So back here where we have Andy and Doreen as Brian and Chris, and Andy and Doreen just as Chris. So we form an array out of those two sets. We'll notice on the next step, we have Andy and Doreen, thank you, has Brian and Chris. So that's all well and good, but this doesn't actually give us our answer because it doesn't. Just trust me. So we need to have a reduce function. The reduce function takes in the key and the value. I called them pair and sets to make them more helpful in this circumstance. And we're going to return the intersection of that. So basically what we're doing is we take in this key value store and replace the value with something else. So the intersection is going to give us eventually what the friends of friends are. I mean, not the friends of friends, the friends in common. So notice Chris is a friend in common there, Andy's a friend in common there, Doreen is there, and there's no friends in common there, sadly. So we end up with our output. MapReduce is kind of funny. You get weird things going on in the middle. The middle results in MapReduce don't necessarily mean a whole lot. That's why it's kind of hard to explain sometimes. But that's how we got to the end. So MapReduce lets you do some really cool stuff without very structured data. So we're going to talk about document stores really quick. Document stores are essentially key value stores, except not. So they are indexed rather than having a key. They can have a primary, it depends on the database. Some of them have primary indexes, some of them just have indexes in general. And the data is deeper. It's for monolithic data. For example, if I want to store a whole ton of info on, like, say, a document, or a Word document. It's a document. A Word document is a great example of this. It has no important information other than itself. It's not related to anything else, but there's a crap ton of information in it. So what we do is we stuff that into a document, and we have a big JSON value to store it. Some document stores are XML-based, but nowadays people are learning from the error of their ways and moving over to JSON. Document stores are also sort of set apart by their really rich querying interface. You can query these things on absolutely any attribute, no matter how deep in the structure it is. You can have an object inside an array, inside an object, inside an array, inside a set, inside a string. Well, no. Flip that. You can't have anything inside a string. So, sorry. And in document stores, MapReduce is sort of secondary because you have this really nice querying interface. You don't need to MapReduce all the time. though it's helpful for large comprehensions. You have aggregation, you have in operators. What separates document stores from SQL, which you're like, okay, well, what's really the difference here? You can store any data type in it, and it can be as deep as you want. There's no schema. You can set up an array inside of it and query the contents of the array, and we're going to get into this. And document stores are also easy to partition. There's no relational data going on, so you can just take chunks and start splitting. You pick an index, and you say, I want this index to be split this way. You can even set up auto partitioning, which is really cool. MongoDB and CouchDB are two very popular document stores. So we're going to sort of take a spin at using the document store for a second. And let's say we want to have a comment system on articles. So users are commenting on articles. We've got three things going on. We've got articles, users, and comments. So maybe one way to approach it would be, okay, I know I shouldn't try to set up relations inside MongoDB because it's not relational. So all right, well, so we'll just put the comments in the user. And we'll say, all right, here's the user, here's his comments. Oh wait, what article is it on? So we violated that. We set up relational data. And the only way you can deal with relational data in a document store is with an extra query. I would get the response from that, say, oh, article ID is 7, and go back out and ask for that article. And then I can finally get things built. Or vice versa, you'd probably go from the article to the ID. But still. So let's try it again. Let's try putting the comments in the article store. All right, so we have our text, an article about HTML5. Here's some comments on it. Here's some text. Oh, wait, we ran into the problem again. We have to query the user now. So we're learning that relational data gets kind of hairy in document stores. Here's another way to do it, and this is going to make you all cringe. We have an article store that has comments and text, and then we wrap the user inside it as well. And we say, here is everything you want to know about the user for the page. And if you really want to get more info about the user, here's the ID, and you can go get more info about them. This is called denormalization, and it kills babies. So what this lets you do is it lets you use all the really fast querying and things like that you get out of a document store without having to worry about relations. Except, what happens if I change my username and I'm no longer JM Renner? Well, then I have to update every single article and every single comment I've ever made. Naturally, this is suboptimal. But then again, if I'm working on a system where data is changing once every year and it's being read 1,000 times an hour, maybe this is sort of okay. And we're going to get to ways to get around this in a second. So data normalization increases speed, introduces consistency issues like we said, and there is no right solution. Because see, when you're dealing with normalized data, I can pose a problem to like 10 people, and I'll probably get about maybe 2 or 3 different ways to represent that data in SQL, but at the end of the day, it's going to be about the same. Because there's just a right way to do things when you're normalizing things. And that's just gone now. And finally, my conclusion here, and some people may beg to differ, but I doubt very many would, is that relational data belongs in a relational database. Don't try to shoehorn something that isn't built to do something. So if it's not built to hold relational data, don't try to make it do that, unless it's really your only option or you're lazy. I sense some judging in the audience. All right, so now we're going to move on to column family stores. And I'm going to preface this with, I have never worked with a column family store outside of theory. So it's going to be light. We're going to move on pretty quick. Column family stores are based on the idea of sort of inverting what you would think of as a regular table. And that makes it really hard, because they use all the words and all the lingo that SQL will use without it meaning the same thing. So when I say a table, tables are a bit different. Tables are defined in terms of column families, which store columns. And it's like, well, what does that mean? I'll have a lovely diagram on the next screen to help explain that. Column families sort of deal in a hierarchy where you have tables, column families, and columns. Tables and column families are defined beforehand. Columns can be declared on the fly inside of a query. Rows are then used to sort of cross-section this and help you find help sort of grab several columns at once, if you are so inclined. Data in column family stores is stored in terms of a key, a value, and a timestamp. This isn't always exposed, but the idea is that it keeps things versioned and safe. Queries on column family stores are also not as robust. You do them in terms of key values and key ranges, and there's some other ways you can query as well. Sometimes they actually support full SQL. It just depends, as always. So this is sort of the idea of what's going on with a column family store. we have these column families of color and of shape. And color could have several attributes. Color can be red, blue, yellow, and it can be stored that way. Color could be stored another way with a name if we wanted to. So the idea is that we created a column family for color, and then a column for red, and a column for blue, and a column for yellow. And the row helps cross-section this, so we can grab it all. These sort of databases are used a lot in things that Google does, where you have to index a lot of data, where the grouping becomes important, and all sorts of very fun things like that. Oh, let me go back a second. Cassandra and HBase are two of the very popular solutions for column family stores. What happened was Google built Bigtable, if you've heard of it, and everyone released the paper, and everyone thought, hey, this is a pretty cool idea, let's build our own. So they've been built. It's exciting. And we're just going to move on from that. So graph databases. Now these are exciting. These are NoSQL's, the NoSQL community's solution to how are we going to deal with relational data. If we don't want to worry about SQL anymore, what can we do? So graph databases are based around the idea of graph theory, where you have vertices and edges. And all of your queries are traversals along this graph. You can look up nodes and vertices via indexes, but then you can grab that and sort of follow it and get to interesting results. It allows for a lot of data discovery. For example, recommendation engines uses, Facebook uses it for graph search and things like that. Facebook uses their own silliness, not any of these databases. But the idea remains that you can find information that you didn't really know was there or were looking for very easily, which is an aspect of SQL as well. For graph databases, Gremlin is the query language of choice. Some databases have implemented their own, but that's really what you're going to be using across all of them. And I apologize, I actually haven't learned Gremlin. I learned Cypher, which was a different one specifically for Neo4j. So I had to go through and learn Gremlin, so I apologize if someone knows Gremlin, and my syntax is awful. But it works, I tested it. So let's say we have this graph, where we have the vertices John and Steve, and we are both people. And we have two other vertices for movies. They're just shaped differently because you can identify what type of vertex you're dealing with. So I figured why not give you that advantage as well. And here we have edges. Let's call these edges a like. I have a like between me and Wizard People Dear Reader. And Steve likes Wizard People Dear Reader as well. But Steve also likes Across the Universe. And you know, I trust people who think like I do. So you know what? Let's see what the people who like the movies I like also like. And I might like them as well. I'll start to provide a recommendation. So we're going to start with a Gremlin query. And we're going to, Gremlin's based on a prompt. It's based on Groovy. So you can actually do some, it looks a lot more like code. So here I create a comment array, and you'll understand why we have that in a bit. All right, so G to start with my graph. I got the first vertex, which is me. I could have a different way to grab the vertex if I didn't know I was the first vertex, but that's just for simplicity. And I grab an edge going out, because this is a directed graph. I can have an undirected graph if I want, but a directed graph is better. Not always, but it can matter here. Because the movie can't like me. That's a little weird. So that's why this is directed. So I grab an out edge, and it's an edge of type like. So these edges actually have type information on them, and I probably should have put them on the side, I apologize. So I grab a like edge, because I can have other edges going to different other things. Like I play a sport, it would be plays, and I want to ignore that. Okay, and so I grab an in vertices. So an edge has an out vertices, so it's coming out of John and going into Dear Reader. So I grab the in vertices. And so it's important to note that here, there's only one movie, but there could be like 100. And Gremlin queries branch is the way they work. So starting from me, I take every edge going out of me that's a like. And now for every one of those edges, I grab that. And for every one of those branches I have in the tree now, I'm going, actually no I'm not, I'm going to store all of those vertices into common. So all of them from all of them, all of those from all the branches gets shoved into common. And this is to make sure later that I don't backtrack on myself. Because I don't want to recommend Wizard People Dear Reader to me if I've already seen it and already said I like it. It's just good practice. So now we're going to get to Steve. We've got to find a way to get to him. So what we're going to do is we're going to follow the arrows into Wizard People Dear Reader. So we're going to grab all the arrows, all the people who say they like it, all the likes, and then we're going to find the vertex that it corresponds to, which in this case would be Steve and me, but I don't want to trust, I trust my own recommendations, but I've already recommended everything, so it won't help me. So we filter out based on the parameter that it being the vertex, it's just a Gremlin convention, its ID does not equal where we started, the first vertex ID, which is me. So we just want to make sure we're not looping back and trusting my own recommendation, because again, then we'll be recommending things we don't want. So now we've gotten to Steve. We've finally gotten to Steve, and all other people who actually like any movie I've ever liked. Finally, we need to get to that last movie. So notice by the way, I'm just compounding these by putting a dot and still writing. You could store them to variables and keep going whatever you wanted to do, but I'm just compounding it into one. So we grab all edges out of Steve. And then we grab all of the movies they relate to. And we say, all right, now we want to exclude any movie that I said I liked, which we stored in common earlier. So now we are onto movies I haven't seen that people who aren't me have liked. And those people who aren't me that have liked those movies also like at least one movie that I liked. Hence this paragraph of query. So at the end of the day, it finally returns to me, I should watch Across the Universe. Now, this query would be a lot simpler in SQL, I think. I haven't sat down and thought about it, but it would probably be about the same, if not easier. But that's because this is a simple example. I could attach a rating to this rather than a like. And I could say, I rate this movie out of 4, Steve rates this movie out of 5, and he rates this movie at a 5. Steve loves this movie. So I can determine that and say, well, is Steve a good enough match with me to trust? I can do that all inside the database query. So graph databases are just a really cool way to express complex understanding of data. It's also important to note that when interacting between John, a rating, and a movie, I would have to do 2 joins on a SQL database. And that's expensive, because I have to compare to every other edge and every other movie. Versus now, starting from John, the only edges I'm going to look at are the edges that I'm connected to. So queries are actually a lot faster over highly relational data than they are on a SQL database. And you say, well, why isn't everybody using these? Well, if you looked at the query, you might understand it's a little complicated. And it's also not an exact science yet. People are still working out how they want these graph databases to work. Their competing standards and things like that. And I actually skipped the names of the databases that are used out there. OrientDB is an open source distributed graph database, which is really cool. Basically, due to the fact that, like I said, the vertices are all direct and I don't have to compare to everything else, I can distribute much more easily because I don't have to compare to everything. And the cost isn't so great when I have to follow a traversal across 2 servers. So Orient's really cool. It's completely open source and distributed, so you can kind of scale however the hell big you want. Then you have Neo4j, which is another really popular one. It supports Cypher, which is a much more convenient query language, where I kind of describe what I want to do, and it figures out the query for me, versus Gremlin, which is very like, this is what I'm doing at every step. Neo4j has great documentation, great community, and that's why they're really popular. But they don't distribute. And at the end of the day, you're capped at about a couple billion, maybe 1 billion, somewhere between 1 and 2 elements. And you're like, wow, well, who's ever going to get to 1 billion? Let me spell some math out for you. Say I have a user. And a user has all sorts of information. They're interacting on the site. They like things. They do things. They have all sorts of bio information. And I want all this to be relatable, which means that I want basically everything to be in a different vertex and it has to have an edge between them. So it's not unreasonable to say that I have 1,000 nodes per user. In fact, that's really not that hard to say at all. And then I get 1 million users. Well, suddenly, my application is capped. It can't go anywhere with Neo4j. So bear that in mind that if you're really planning to scale, Neo4j is going to cause you problems. Their solution is they say, oh, well, you shouldn't need more than 1 billion nodes on 1 graph. Just spin up 2 graphs, keep them distinct. I think that limits the spirit of graph databases, which is that all data can be related in some way. So, not all data, some things will be separate. But anyway, I err towards OrientDB. So back through all of this, sorry about that. So sort of a little bit of recap. NoSQL is based on the idea of base. So we're focused on availability and partition tolerance, not consistency. So it's a big change for a lot of people. We have 4 types. We have key value stores, document stores, column families, and graph databases. And really the final takeaway is there is no magic bullet. I would say the closest is the graph database. But really the idea is that you can't say, this is the database to use for all problems. Because each database is going to have its own strengths and its own weaknesses, and you're going to have to compensate for them. Otherwise, it wouldn't be engineering, it would be playtime. So, if you guys have any questions, I have a bit more I can talk about, but I'll stop for questions. Yes, you, sir.
So what if I was trying to do a whole bunch of reads, or not reads, writes, so like just pieces of data into the database. Mm-hmm. Which one of these is going to be the most performant, or are none of them?
Okay, these are actually all very performant for writes. Well, straight writes, very performant, because there's no relational data that has to be compiled on a write. I literally just take the data and I just go thunk and throw it in where it needs to go. But with document stores, say I'm trying to update something, updates become costly with document stores because you have really deep structures, and I could be updating something that's way, way, way down, and that takes more time than it would on a lot of other databases. Yeah. A bit about graph databases. Graph databases are typically built on something like a document store or key value store. Honestly, the difference between these two is this one does more than that one does, and that makes that one more lightweight, but there's really no clear distinction between them in the way they work. Graph databases are built on top of one of the other, which means that all the querying speed you have, if you're not using any of the relational features, is basically there. So you get the fast lookups you would get on a key value or document store because you can index on a lot of them anyway. And that is very helpful. All of these are schemaless, except for column families, which have a bit of a schema to them in that column families are predefined, but columns are not. So I kind of threw a ton of information at you, and that's kind of all I got. And if you guys don't have questions, I guess thank you.